Chapter 12. Transition to multi-engine airplanes. Introduction. This chapter is devoted to the factors associated with the operation of small multi-engine airplanes. For the purpose of this handbook, a small multi-engine airplane is a reciprocating or turbopropeller-powered airplane with a maximum certificated takeoff weight of 12,500 pounds or less. This discussion assumes a conventional design with two engines, one mounted on each wing. Reciprocating engines are assumed unless otherwise noted. The term light twin, although not formally defined in the regulations, is used herein as a small multi-engine airplane with a maximum certificated takeoff weight of 6,000 pounds or less. There are several unique characteristics of multi-engine airplanes that make them worthy of a separate class rating. Knowledge of these factors and proficient flight skills are a key to safe flight in these airplanes. This chapter deals extensively with the numerous aspects of one-engine inoperative, OEI, flight. However, pilots are strongly cautioned not to place undue emphasis on mastery of OA flight as the sole key to flying multi-engine airplanes safely. The inoperative engine information that follows is extensive only because this chapter emphasizes the differences between flying multi-engine airplanes as contrasted to single-engine airplanes. 12-1. The modern, well-equipped multi-engine airplane can be remarkably capable under many circumstances. But, as with single-engine airplanes, it must be flown prudently by a current and competent pilot to achieve the highest possible level of safety. This chapter contains information and guidance on the performance of certain maneuvers and procedures in small multi-engine airplanes for the purposes of flight training and pilot certification testing. The airplane manufacturer is the final authority on the operation of a particular make and model airplane. Flight instructors and students should use the Federal Aviation Administration's Approved Flight Manual, AFM, and/or the Pilot's Operating Handbook, POH, but realize that the airplane manufacturer's guidance and procedures take precedence. The basic difference between operating a multi-engine airplane and a single-engine airplane is the potential problem involving an engine failure. The penalties for loss of an engine are twofold: performance and control. The most obvious problem is the loss of 50% of power, which reduces climb performance 80 to 90%, sometimes even more. The other is the control problem caused by the remaining thrust, which is now asymmetrical. Attention to both these factors is crucial to safe OA flight. The performance and systems redundancy of a multi-engine airplane is a safety advantage only to a trained and proficient pilot. Terms and definitions. Pilots of single-engine airplanes are already familiar with many performance V-speeds and their definitions. Twin-engine airplanes have several additional V-speeds unique to OA operation. These speeds are differentiated by the notation SE for single-engine. A review of some key V-speeds and several new V-speeds unique to twin-engine airplanes are listed below. VR, rotation speed, speed at which back pressure is applied to rotate the airplane to a takeoff attitude. VLOOF, liftoff speed, speed at which the airplane leaves the surface. Note, some manufacturers reference takeoff performance data to VR, others to VLOOF. VX, best angle of climb speed, speed at which the airplane gains the greatest altitude for a given distance of forward travel. VXSE, best angle of climb speed with OA. VY, best rate of climb speed, speed at which the airplane gains the most altitude for a given unit of time. VICE, best rate of climb speed with OA. Marked with a blue radial line on most airspeed indicators. Above the single-engine absolute ceiling, VICE yields the minimum rate of sink. VSSE, safe, intentional OA speed, originally known as safe single-engine speed, now formally defined in Title 14 of the Code of Federal Regulations, 14 CFR, Part 23, Airworthiness Standards, and required to be established and published in the AFM/PO. It is the minimum speed to intentionally render the critical engine inoperative. VRF, reference landing speed, an airspeed used for final approach, which adjusts the normal approach speed for winds and gusty conditions. VRF is 1.3 times the stall speed in the landing configuration. VMC, minimum control speed with the critical engine inoperative, marked with a red radial line on most airspeed indicators. The minimum speed at which directional control can be maintained under a very specific set of circumstances outlined in 14 CFR Part 23, Airworthiness Standards. Under the small airplane certification regulations currently in effect, the flight test pilot must be able to 1. Stop the turn that results when the critical engine is suddenly made inoperative within 20 degrees of the original heading, using maximum rudder deflection and a maximum of 5 degrees bank, and 2. Thereafter, maintain straight flight with not more than a 5 degrees bank. There is no requirement in this determination that the airplane be capable of climbing at this airspeed. VMC only addresses directional control. Further discussion of VMC is determined during airplane certification and demonstrated in pilot training follows in minimum control airspeed, VMC, demonstration. Figure 12.1. Unless otherwise noted, when V speeds are given in the AFM/PO, they apply to sea level, standard day conditions at maximum takeoff weight. Performance speeds vary with aircraft weight, configuration, and atmospheric conditions. The speeds may be stated in statute miles per hour, mile per hour, or knots, kt, and they may be given as calibrated airspeeds, CAS, or indicated airspeeds, IAS. As a general rule, the newer AFM/PO show V speeds in knots indicated airspeed, KIAS. Some V speeds are also stated in knots calibrated airspeed, KCAS, to meet certain regulatory requirements. Whenever available, pilots should operate the airplane from published indicated airspeeds. With regard to climb performance, the multi-engine airplane, particularly in the takeoff or landing configuration, may be considered to be a single-engine airplane with its power plant divided into 2 units. There is nothing in 14 CFR Part 23 that requires a multi-engine airplane to maintain altitude while in the takeoff or landing configuration with OA. In fact, 12:2 is 40 airspeed, knots, 260, 250, 0, 0, 2, 60, 80, 160, 041, 140, TAS, 100, 120, 200, 180, 160. Figure 12:1. Airspeed indicator markings for a multi-engine airplane. Many twins are not required to do this in any configuration, even at sea level. The current 14 CFR Part 23 single-engine climb performance requirements for reciprocating engine-powered multi-engine airplanes are as follows. More than 6,000 pounds maximum weight in or VSO more than 61 knots, the single-engine rate of climb in feet per minute, FPM, at 5,000 feet mean sea level, MSL, must be equal to at least 0.027 VSO2. For airplanes type certificated February 4, 1991, or thereafter, the climb requirement is expressed in terms of a climb gradient, 1.5%. The climb gradient is not a direct equivalent of the 0.027 VSO2 formula. Do not confuse the date of type certification with the airplane's model year. The type certification basis of many multi-engine airplanes dates back to the Civil Aviation Regulations, CAR, 3. 6,000 pounds or less maximum weight and VSO 61 knots or less, the single-engine rate of climb at 5,000 feet MSL must simply be determined. The rate of climb could be a negative number. There is no requirement for a single-engine positive rate of climb at 5,000 feet or any other altitude. For light twins type certificated February 4, 1991, or thereafter, the single-engine climb gradient, positive or negative, is simply determined. Rate of climb is the altitude gain per unit of time, while climb gradient is the actual measure of altitude gain per 100 feet of horizontal travel, expressed as a percentage. An altitude gain of 1.5 feet per 100 feet of travel, or 15 feet per 1,000, or 150 feet per 10,000, is a climb gradient of 1.5%. There is a dramatic performance loss associated with the loss of an engine, particularly just after takeoff. Any airplane's climb performance is a function of thrust horsepower, which is in excess of that required for level flight. In a hypothetical twin with each engine producing 200 thrust horsepower, assume that the total level flight thrust horsepower required is 175. In this situation, the airplane would ordinarily have a reserve of 225 thrust horsepower available for climb. Loss of one engine would leave only 25, 200 minus 175, thrust horsepower available for climb, a drastic reduction. Sea level rate of climb performance losses of at least 80 to 90%, even under ideal circumstances, are typical for multi-engine airplanes in OA flight. Operation of systems. This section deals with systems that are generally found on multi-engine airplanes. Multi-engine airplanes share many features with complex single-engine airplanes. There are certain systems and features covered that are generally unique to airplanes with two or more engines. Propellers. The propellers of the multi-engine airplane may outwardly appear to be identical in operation to the constant-speed propellers of many single-engine airplanes, but this is not the case. The propellers of multi-engine airplanes are featherable, to minimize drag in the event of an engine failure. Depending upon single-engine performance, this feature often permits continued flight to a suitable airport following an engine failure. To feather a propeller is to stop engine rotation with the propeller blades streamlined with the airplane's relative wind, thus to minimize drag. Figure 12.2. Feathering is necessary because of the change in parasite drag with propeller blade angle. Figure 12.3. When the propeller blade angle is in the feathered position, the change in parasite drag is at a minimum and, in the case of a typical multi-engine airplane, the added parasite drag from a single feathered propeller is a relatively small contribution to the airplane total drag. At the smaller blade angles near the flat pitch position, the drag added by the propeller is very large. At these small blade angles, the propeller windmilling at high rates per minute, RPM, can create such a tremendous amount of drag that the airplane may be uncontrollable. The propeller windmilling at high speed in the low range of blade angles can produce an increase in parasite drag, which may be as great as the parasite drag of the basic airplane. 12.3. GARD. ETISARP. L. I. TNEAVUQE. NI. EGNAHC. W. I. N. D. M. I. L. L. I. N. G. P. R. O. P. E. L. L. E. R. Stationary propeller. Flat blade position. Feathered position. 0. 15. 45. 30-60 propeller blade angle. 90. Figure 12.3. Propeller drag contribution. The counterweights is generally slightly greater than the aerodynamic forces. Oil pressure from the propeller governor is used to counteract the counterweights and drives the blade angles to low pitch, high RPM. A reduction in oil pressure causes the RPM to be reduced from the influence of the counterweights. Figure 12.4. To feather the propeller control is brought fully aft. All oil pressure is dumped from the governor, and the counterweights drive the propeller blades towards feather. As centrifugal force acting on the counterweights decays from decreasing RPM, additional forces are needed to completely feather the blades. This additional force comes from either a spring or high-pressure air stored in the propeller dome, which forces the blades into the feathered position. The entire process may take up to 10 seconds. Feathering a propeller only alters blade angle and stops engine rotation. To completely secure the engine, the pilot must still turn off the fuel, mixture, electric boost pump, and fuel selector, ignition, alternator/generator, and close the cowl flaps. If the airplane is pressurized, there may also be an air bleed to close for the failed engine. Some airplanes are equipped with firewall shutoff valves that secure several of these systems with a single switch. Completely securing a failed engine may not be necessary or even desirable depending upon the failure mode, altitude, and time available. The position of the fuel controls, ignition, and alternator/generator switches of the failed engine has no effect on aircraft performance. There is always the distinct possibility of manipulating the incorrect switch under conditions of haste or pressure. To unfeather a propeller, the engine must be rotated so that oil pressure can be generated to move the propeller blades. Low pitch. High pitch. Full feathered 90 degrees. Figure 12.2. Feathered propeller. As a review, the constant speed propellers on almost all single-engine airplanes are of the non-feathering, oil pressure to increase pitch design. In this design, increased oil pressure from the propeller governor drives the blade angle towards high pitch, low RPM. In contrast, the constant speed propellers installed on most multi-engine airplanes are full feathering, counterweighted, oil pressure to decrease pitch designs. In this design, increased oil pressure from the propeller governor drives the blade angle towards low pitch, high RPM, away from the feather blade angle. In effect, the only thing that keeps these propellers from feathering is a constant supply of high-pressure engine oil. This is a necessity to enable propeller feathering in the event of a loss of oil pressure or propeller governor failure. The aerodynamic forces alone acting upon a windmilling propeller tend to drive the blades to low pitch, high RPM. Counterweights attached to the shank of each blade tend to drive the blades to high pitch, low RPM. Inertia, or apparent force, called centrifugal force, acting through 12 to 4. 1. 4. Counterweight action. 6. Hydraulic force. Aerodynamic force. Nitrogen pressure or spring force, and counterweight action. 4. 5. 6. The forks push the pitch change pin of each blade toward the front of the hub, causing the blades to twist toward the low pitch position. A nitrogen pressure charge or mechanical spring in the front of the hub opposes the oil pressure and causes the propeller to move toward high pitch. Counterweights also cause the blades to move toward the high pitch and feather positions. The counterweights counteract the aerodynamic twisting force that tries to move the blades toward a low pitch angle. 6. 2 3. 5. 1. 2. 3. High pressure oil enters the cylinder through the center of the propeller shaft and piston rod. The propeller control regulates the flow of high pressure oil from a governor. A hydraulic piston in the hub of the propeller is connected to each blade by a piston rod. This rod is attached to forks that slide over the pitch change pin mounted in the root of each blade. The oil pressure moves the piston toward the front of the cylinder, moving the piston rod and forks forward. Figure 12.4. Pitch change forces. From the feathered position, the ignition is turned on prior to engine rotation with the throttle at low idle and the mixture rich. With the propeller control in a high RPM position, the starter is engaged. The engine begins to windmill, start, and run as oil pressure moves the blades out of feather. As the engine starts, the propeller RPM should be immediately reduced until the engine has had several minutes to warm up. The pilot should monitor cylinder head and oil temperatures. Pin senses a lack of centrifugal force from propeller rotation and falls into place, preventing the blades from feathering. Therefore, if a propeller is to be feathered, it must be done before engine RPM decays below approximately 800. On one popular model of turboprop engine, the propeller blades do, in fact, feather with each shutdown. This propeller is not equipped with such centrifugally operated pins due to a unique engine design. In any event, the AFM/POPE procedures should be followed for the exact unfeathering procedure. Both feathering and starting a feathered reciprocating engine on the ground are strongly discouraged by manufacturers due to the excessive stress and vibrations generated. As just described, a loss of oil pressure from the propeller governor allows the counterweights, spring, and/or dome charge to drive the blades to feather. Logically then, the propeller blade should feather every time an engine is shut down as oil pressure falls to zero. Yet, this does not occur. Preventing this is a small pin in the pitch-changing mechanism of the propeller hub that does not allow the propeller blades to feather once RPM drops below approximately 800. An unfeathering accumulator is a device that permits starting a feathered engine in flight without the use of the electric starter. An accumulator is any device that stores a reserve of high pressure. On multi-engine airplanes, the unfeathering accumulator stores a small reserve of engine oil under pressure from compressed air or nitrogen. To start a feathered engine in flight, the pilot moves the propeller control out of the feather position to release the accumulator pressure. The oil flows under pressure to the propeller hub and drives the blades toward the high RPM, low pitch position, whereupon the propeller usually begins to windmill. On some airplanes, an assist from the electric starter may be necessary to initiate rotation and completely unfeather the propeller. If fuel and ignition are present, the engine starts and runs. For airplanes 12 to 5. Used in training, this saves much electric starter and battery wear. High oil pressure from the propeller governor recharges the accumulator just moments after engine rotation begins. Propeller synchronization. Many multi-engine airplanes have a propeller synchronizer, prop sync, installed to eliminate the annoying drumming or beat of propellers whose RPM are close, but not precisely the same. To use prop sync, the propeller RPM is coarsely matched by the pilot and the system is engaged. The prop sync adjusts the RPM of the slave engine to precisely match the RPM of the master engine and then maintains that relationship. The prop sync should be disengaged when the pilot selects a new propeller RPM and then re-engaged after the new RPM is set. The prop sync should always be off for takeoff, landing, and single engine operation. The AFM/PO should be consulted for system description and limitations. A variation on the propeller synchronizer is the propeller synchrophaser. Prop synchrophase acts much like a synchronizer to precisely match RPM, but the synchrophaser goes one step further. It not only matches RPM but actually compares and adjusts the positions of the individual blades of the propellers in their arcs. There can be significant propeller noise and vibration reductions with a propeller synchrophaser. From the pilot's perspective, operation of a propeller synchronizer and a propeller synchrophaser are very similar. A synchrophaser is also commonly referred to as prop sync, although that is not entirely correct nomenclature from a technical standpoint. As a pilot aid to manually synchronizing the propellers, some twins have a small gauge mounted in or by the tachometers with a propeller symbol on a disc that spins. The pilot manually fine-tunes the engine RPM so as to stop disc rotation, thereby synchronizing the propellers. This is a useful backup to synchronizing engine RPM using the audible propeller beat. This gauge is also found installed with most propeller synchronizer and synchrophase systems. Some synchrophase systems use a knob for the pilot to control the phase angle. Fuel crossfeed systems are also unique to multi-engine airplanes. Using crossfeed, an engine can draw fuel from a fuel tank located in the opposite wing. On most multi-engine airplanes, operation in the crossfeed mode is an emergency procedure used to extend airplane range and endurance in OA flight. There are a few models that permit crossfeed as a normal, fuel balancing technique in normal operation, but these are not common. The AFM-PO describes crossfeed limitations and procedures that vary significantly among multi-engine airplanes. Checking crossfeed operation on the ground with a quick repositioning of the fuel selectors does nothing more than ensure freedom of motion of the handle. To actually check crossfeed operation, a complete, functional crossfeed system check should be accomplished. To do this, each engine should be operated from its crossfeed position during the run-up. The engines should be checked individually and allowed to run at moderate power, 1,500 revolutions per minute minimum, for at least 1 minute to ensure that fuel flow can be established from the crossfeed source. Upon completion of the check, each engine should be operated for at least 1 minute at moderate power from the main, takeoff, fuel tanks to reconfirm fuel flow prior to takeoff. This suggested check is not required prior to every flight. Crossfeed lines are ideal places for water and debris to accumulate unless they are used from time to time and drained using their external drains during pre-flight. Crossfeed is ordinarily not used for completing single-engine flights when an alternate airport is readily at hand, and it is never used during takeoff or landings. Combustion heaters are common on multi-engine airplanes. A combustion heater is best described as a small furnace that burns gasoline to produce heated air for occupant comfort and windshield defogging. Most are thermostatically operated and have a separate hour meter to record time in service for maintenance purposes. Automatic over-temperature protection is provided by a thermal switch mounted on the unit that cannot be accessed in flight. This requires the pilot or mechanic to actually visually inspect the unit for possible heat damage in order to reset the switch. When finished with the combustion heater, a cool-down period is required. Most heaters require that outside air be permitted to circulate through the unit for at least 15 seconds in flight or that the ventilation fan can be operated for at least 2 minutes on the ground. Failure to provide an adequate cool-down usually trips the thermal switch and renders the heater inoperative until the switch is reset. Flight Director/Autopilot FD/AP systems are common on the better-equipped multi-engine airplanes. The system integrates pitch, roll, heading, altitude, and radio navigation signals in a computer. The outputs, called computed commands, are displayed on a Flight Command Indicator, FCI. The FCI replaces the conventional attitude indicator on the instrument panel. The FCI is occasionally referred to as a Flight Director Indicator, FDI, or as an Attitude Director Indicator, ADI. 12-6. The entire Flight Director/Autopilot system is sometimes called an Integrated Flight Control System, IFCS, by some manufacturers. Others may use the term Automatic Flight Control System, AFCS. The FD/AP system may be employed at the following different levels. Off, raw data. Flight Director, computed commands. Autopilot. With the system off, the FCI operates as an ordinary attitude indicator. On most FCIs, the command bars are biased out of view when the FD is off. The pilot maneuvers the airplane as though the system were not installed. To maneuver the airplane using the FD, the pilot enters the desired modes of operation: heading, altitude, navigation, NAV, intercept, and tracking, on the FD/AP mode controller. The computed flight commands are then displayed to the pilot through either a single queue or dual queue system in the FCI. On a single queue system, the commands are indicated by V bars. On a dual queue system, the commands are displayed on two separate command bars, one for pitch and one for roll. To maneuver the airplane using computed commands, the pilot flies the symbolic airplane of the FCI to match the steering cues presented. On most systems, to engage the autopilot, the FD must first be operating. At any time thereafter, the pilot may engage the autopilot through the mode controller. The autopilot then maneuvers the airplane to satisfy the computed commands of the FD. Like any computer, the FD/AP system only does what it is told. The pilot must ensure that it has been programmed properly for the particular phase of flight desired. The armed in or engaged modes are usually displayed on the mode controller or separate annunciator lights. When the airplane is being hand-flown, if the FD is not being used at any particular moment, it should be off so that the command bars are pulled from view. Prior to system engagement, all FD/AP computer and trim checks should be accomplished. Many newer systems cannot be engaged without the completion of a self-test. The pilot must also be very familiar with various methods of disengagement, both normal and emergency. System details, including approvals and limitations, can be found in the supplements section of the AFM/PO. Additionally, many avionics manufacturers can provide informative pilot operating guides upon request. Yaw damper. The yaw damper is a servo that moves the rudder in response to inputs from a gyroscope or accelerometer that detects yaw rate. The yaw damper minimizes motion about the vertical axis caused by turbulence. Yaw dampers on swept-wing airplanes provide another, more vital function of damping Dutch roll characteristics. Occupants feel a smoother ride, particularly if seated in the rear of the airplane, when the yaw damper is engaged. The yaw damper should be off for takeoff and landing. There may be additional restrictions against its use during single-engine operation. Most yaw dampers can be engaged independently of the autopilot. Alternator/generator. Alternator or generator paralleling circuitry matches the output of each engine's alternator/generator so that the electrical system load is shared equally between them. In the event of an alternator/generator failure, the inoperative unit can be isolated and the entire electrical system powered from the remaining one. Depending upon the electrical capacity of the alternator/generator, the pilot may need to reduce the electrical load, referred to as load shedding, when operating on a single unit. The AFM/PO contains system description and limitations. Nose baggage compartment. Nose baggage compartments are common on multi-engine airplanes, and are even found on a few single-engine airplanes. There is nothing strange or exotic about a nose baggage compartment, and the usual guidance concerning observation of load limits applies. Pilots occasionally neglect to secure the latches properly. When improperly secured, the door opens and the contents may be drawn out, usually into the propeller arc and just after takeoff. Even when the nose baggage compartment is empty, airplanes have been lost when the pilot became distracted by the open door. Security of the nose baggage compartment latches and locks is a vital pre-flight item. Most airplanes continue to fly with the nose baggage door open. There may be some buffeting from the disturbed airflow, and there is an increasing noise. Pilots should never become so preoccupied with an open door, of any kind, that they fail to fly the airplane. Inspection of the compartment interior is also an important pre-flight item. More than one pilot has been surprised to find a supposedly empty compartment packed to capacity or loaded with ballast. The tow bars, engine inlet covers, windshield sunscreens, oil containers, spare chocks, and miscellaneous small hand tools that find their way into baggage compartments should be secured to prevent damage from shifting in flight. 12-7. Usually plumbed to a non-pressurized baggage compartment. The pilot must activate the alternate static source by opening a valve or a fitting in the flight deck. Upon activation, the airspeed indicator, altimeter, and the vertical speed indicator, VSI, is affected and reads somewhat in error. A correction table is frequently provided in the AFM/PO. Anti-icing/de-icing equipment only eliminates ice from the protected surfaces. Significant ice accumulations may form on unprotected areas, even with proper use of anti-ice and de-ice systems. Flight at high angles of attack, AOA, or even normal climb speeds permit significant ice accumulations on lower wing surfaces, which are unprotected. Many AFM posts mandate minimum speeds to be maintained in icing conditions. Degradation of all flight characteristics and large performance losses can be expected with ice accumulations. Pilots should not rely upon the stall warning devices for adequate stall warning with ice accumulations. Ice accumulates unevenly on the airplane. It adds weight and drag, primarily drag, and decreases thrust and lift. Even wing shape affects ice accumulation. Thin airfoil sections are more prone to ice accumulation than thick, highly cambered sections. For this reason, certain surfaces, such as the horizontal stabilizer, are more prone to icing than the wing. With ice accumulations, landing approaches should be made with a minimum wing flap setting. Flap extension increases the OA of the horizontal stabilizer, and with an added margin of airspeed. Sudden and large configuration and airspeed changes should be avoided. Unless otherwise recommended in the AFM/PO, the autopilot should not be used in icing conditions. Continuous use of the autopilot masks trim and handling changes that occur with ice accumulation. Without this control feedback, the pilot may not be aware of ice accumulation building to hazardous levels. The autopilot suddenly disconnects when it reaches design limits, and the pilot may find the airplane has assumed unsatisfactory handling characteristics. The installation of anti-ice/DAS equipment on airplanes without AFM/PO approval for flight into icing conditions is to facilitate escape when such conditions are inadvertently encountered. Even with AFM/PO approval, the prudent pilot avoids icing conditions to the maximum extent practicable and avoids extended flight in any icing conditions. No multi-engine airplane is approved for flight into severe icing conditions, and none are intended for indefinite flight in continuous icing conditions. Anti-icing/deicing Anti-icing/deicing equipment is frequently installed on multi-engine airplanes and consists of a combination of different systems. These may be classified as either anti-icing or deicing, depending upon function. The presence of anti-icing and deicing equipment, even though it may appear elaborate and complete, does not necessarily mean that the airplane is approved for flight in icing conditions. The AFM/PO, placards, and even the manufacturer should be consulted for specific determination of approvals and limitations. Anti-icing equipment is provided to prevent ice from forming on certain protected surfaces. Anti-icing equipment includes heated pitot tubes, heated or non-icing static ports and fuel vents, propeller blades with electrothermal boots or alcohol slingers, windshields with alcohol spray or electrical resistance heating, windshield defoggers, and heated stall warning lift detectors. On many turboprop engines, the lip surrounding the air intake is heated either electrically or with bleed air. In the absence of AFM/PO guidance to the contrary, anti-icing equipment should be actuated prior to flight into known or suspected icing conditions. Deicing equipment is generally limited to pneumatic boots on wing and tail leading edges. Deicing equipment is installed to remove ice that has already formed on protected surfaces. Upon pilot actuation, the boots inflate with air from the pneumatic pumps to break off accumulated ice. After a few seconds of inflation, they are deflated back to their normal position with the assistance of a vacuum. The pilot monitors the buildup of ice and cycles the boots as directed in the AFM/PO. An ice light on the left engine nacelle allows the pilot to monitor wing ice accumulation at night. Other airframe equipment necessary for flight in icing conditions includes an alternate induction air source and an alternate static system source. Ice-tolerant antennas are also installed. In the event of impact ice accumulating over normal engine air induction sources, carburetor heat, carbureted engines, or alternate air, fuel-injected engines, should be selected. Ice buildup on normal induction sources can be detected by a loss of engine RPM with fixed-pitch propellers and a loss of manifold pressure with constant-speed propellers. On some fuel-injected engines, an alternate air source is automatically activated with blockage of the normal air source. An alternate static system provides an alternate source of static air for the pitot-static system in the unlikely event that the primary static source becomes blocked. In non-pressurized airplanes, most alternate static sources are plumbed to the cabin. On pressurized airplanes, they are 12-8. Performance and limitations. Discussion of performance and limitations requires the definition of the following terms. Accelerate stop distance is the runway length required to accelerate to a specified speed, either VR or VLOF, as specified by the manufacturer. Experience an engine failure, and bring the airplane to a complete stop. Accelerate go distance is the horizontal distance required to continue the takeoff and climb to 50 feet, assuming an engine failure at VR or VLOF, as specified by the manufacturer. Climb gradient is a slope most frequently expressed in terms of altitude gain per 100 feet of horizontal distance, whereupon it is stated as a percentage. A 1.5% climb gradient is an altitude gain of 1.5 feet per 100 feet of horizontal travel. Climb gradient may also be expressed as a function of altitude gain per nautical mile nm, or as a ratio of the horizontal distance to the vertical distance, 50:1, for example. Unlike rate of climb, climb gradient is affected by wind. Climb gradient is improved with a headwind component and reduced with a tailwind component. Figure 12.5. The all-engine service ceiling of multi-engine airplanes is the highest altitude at which the airplane can maintain a steady rate of climb of 100 fpm with both engines operating. The airplane has reached its absolute ceiling when climb is no longer possible. The single-engine service ceiling is reached when the multi-engine airplane can no longer maintain a 50 fpm rate of climb with OA, and its single-engine absolute ceiling when climb is no longer possible. The takeoff in a multi-engine airplane should be planned in sufficient detail so that the appropriate action is taken in the event of an engine failure. The pilot should be thoroughly familiar with the airplane's performance capabilities and limitations in order to make an informed takeoff decision as part of the pre-flight planning. That decision should be reviewed as the last item of the before takeoff checklist. In the event of an engine failure shortly after takeoff, the decision is basically one of continuing flight or landing, even off airport. If single-engine climb performance is adequate for continued flight, and the airplane has been promptly and correctly configured, the climb after takeoff may be continued. If single-engine climb performance is such that climb is unlikely or impossible, a landing has to be made in the most suitable area. To be avoided above all is attempting to continue flight when it is not within the airplane's performance capability to do so. Figure 12.6. Accelerate go distance. VR/VLOF. 50 feet. Brake release. Accelerate stop distance. Brake release. VLOF. Figure 12.5. Accelerate stop distance, accelerate go distance, and climb gradient. 5,000 feet. 10:1 or 10% climb gradient. 500 feet. 12:9. Takeoff planning factors include weight and balance, airplane performance, both single and multi-engine, runway length, slope and contamination, terrain and obstacles in the area, weather conditions, and pilot proficiency. Most multi-engine airplanes have AFM/PO performance charts and the pilot should be highly proficient in their use. Prior to takeoff, the multi-engine pilot should ensure that the weight and balance limitations have been observed, the runway length is adequate, and the normal flight path clears obstacles and terrain. A clear and definite course of action to follow in the event of engine failure is essential. The regulations do not specifically require that the runway length be equal to or greater than the accelerate stop distance. Most AFM/POs publish accelerate stop distances only as an advisory. It becomes a limitation only when published in the limitations section of the AFM/PO. Experienced multi-engine pilots, however, recognize the safety margin of runway lengths in excess of the bare minimum required for normal takeoff. They insist on runway lengths of at least accelerate stop distance as a matter of safety and good operating practice. The multi-engine pilot must keep in mind that the accelerate go distance, as long as it is, has only brought the airplane, under ideal circumstances, to a point a mere 50 feet above the takeoff elevation. To achieve even this meager climb, the pilot had to instantaneously recognize and react to an unanticipated engine failure, retract the landing gear, identify and feather the correct engine, all the while maintaining precise airspeed control and bank angle as the airspeed is nursed to vice. Assuming flawless airmanship thus far, the airplane has now arrived at a point little more than one wingspan above the terrain, assuming it was absolutely level and without obstructions. For the purpose of illustration, with a near 150 fpm rate of climb at a 90-knot vice, it takes approximately 3 minutes to climb an additional 450 feet to reach 500 feet AGL. In doing so, the airplane has traveled an additional 5 nautical miles beyond the original accelerate go distance, with a climb gradient of about 1.6%. Any turn, such as to return to the airport, seriously degrades the already marginal climb performance of the airplane. Not all multi-engine airplanes have published accelerate go distances in their AFM/PO, and fewer still publish climb gradients. When such information is published, the figures have been determined under ideal flight testing conditions. It is unlikely that this performance is duplicated in service conditions. The point of the previous discussion is to illustrate the marginal climb performance of a multi-engine airplane that suffers an engine failure shortly after takeoff, even under ideal conditions. The prudent multi-engine pilot should pick a decision point in the takeoff and climb sequence in advance. If an engine fails before this point, the takeoff should be rejected, even if airborne, for a landing on whatever runway or surface lies essentially ahead. If an engine fails after this point, the pilot should promptly execute the appropriate engine failure procedure and continue the climb, assuming the performance capability exists. As a general recommendation, if the landing gear has not been selected up, the takeoff should be rejected, even if airborne. As a practical matter for planning purposes, the option of continuing the takeoff probably does not exist unless the published single-engine rate of climb performance is at least 100 to 200 fpm. Thermal turbulence, wind gusts, engine and propeller wear, or poor technique in airspeed, bank angle, and rudder control can easily negate even a 200 fpm rate of climb. A pre-takeoff safety brief clearly defines all pre-planned emergency actions to all crew members. Even if operating the aircraft alone, the pilot should review and be familiar with takeoff emergency considerations. Indecision at the moment an emergency occurs degrades reaction time and the ability to make a proper response. VR/FLOOF. Best angle of climb VXSE. Best rate of climb VICE. Brake release. Decision area. E. GIN. N. EE. N. SOFO. S. DLO. N. PA. RU. A. GE. Figure 12.6. Area of decision for engine failure after liftoff. 12 to 10. Weight and balance. The weight and balance concept is no different than that of a single-engine airplane. The actual execution, however, is almost invariably more complex due to a number of new loading areas, including nose and aft baggage compartments, nacelle lockers, main fuel tanks, auxiliary fuel tanks, nacelle fuel tanks, and numerous seating options in a variety of interior configurations. The flexibility in loading offered by the multi-engine airplane places a responsibility on the pilot to address weight and balance prior to each flight. The terms empty weight, licensed empty weight, standard empty weight, and basic empty weight as they appear on the manufacturer's original weight and balance documents are sometimes confused by pilots. In 1975, the General Aviation Manufacturers Association, GAMA, adopted a standardized format for AFM/POs. It was implemented by most manufacturers in model year 1976. Airplanes whose manufacturers conform to the GAMA standards utilize the following terminology for weight and balance. Standard empty weight plus optional equipment equals basic empty weight. Standard empty weight is the weight of the standard airplane, full hydraulic fluid, unusable fuel, and full oil. Optional equipment includes the weight of all equipment installed beyond standard. Basic empty weight is the standard empty weight plus optional equipment. Note that basic empty weight includes no usable fuel, but full oil. Airplanes manufactured prior to the GAMA format generally utilize the following terminology for weight and balance, although the exact terms may vary somewhat. Empty weight plus unusable fuel equals standard empty weight. Standard empty weight plus optional equipment equals licensed empty weight. Empty weight is the weight of the standard airplane, full hydraulic fluid, and undrainable oil. Unusable fuel is the fuel remaining in the airplane not available to the engines. Standard empty weight is the empty weight plus unusable fuel. When optional equipment is added to the standard empty weight, the result is licensed empty weight. Licensed empty weight, therefore, includes the standard airplane, optional equipment, full hydraulic fluid, unusable fuel, and undrainable oil. The major difference between the two formats, GAMA and the old, is that basic empty weight includes full oil and licensed empty weight does not. Oil must always be added to any weight and balance utilizing a licensed empty weight. When the airplane is placed in service, amended weight and balance documents are prepared by appropriately rated maintenance personnel to reflect changes in installed equipment. The old weight and balance documents are customarily marked superseded and retained in the AFM/PO. Maintenance personnel are under no regulatory obligation to utilize the GAMA terminology, so weight and balance documents subsequent to the original may use a variety of terms. Pilots should use care to determine whether or not oil has to be added to the weight and balance calculations or if it is already included in the figures provided. The multi-engine airplane is where most pilots encounter the term zero fuel weight for the first time. Not all multi-engine airplanes have a zero fuel weight limitation published in their AFM/PO, but many do. Zero fuel weight is simply the maximum allowable weight of the airplane and payload, assuming there is no usable fuel on board. The actual airplane is not devoid of fuel at the time of loading, of course. This is merely a calculation that assumes it was. If a zero fuel weight limitation is published, then all weight in excess of that figure must consist of usable fuel. The purpose of a zero fuel weight is to limit load forces on the wing spars with heavy fuselage loads. Assume a hypothetical multi-engine airplane with the following weights and capacities. Basic empty weight. 3,200 pounds zero fuel weight. 4,400 pounds maximum takeoff weight. 5,200 pounds maximum usable fuel. 180 gallons. 1. Calculate the useful load. Maximum takeoff weight. 5,200 pounds basic empty weight. Minus 3,200 pound useful load. 2,000 pounds. The useful load is the maximum combination of usable fuel, passengers, baggage, and cargo that the airplane is capable of carrying. 2. Calculate the payload. Zero fuel weight. 4,400 pounds basic empty weight. Minus 3,200 pound payload. 1,200 pounds. 12 to 11. The payload is the maximum combination of passengers, baggage, and cargo that the airplane is capable of carrying. A zero fuel weight, if published, is the limiting weight. 3. Calculate the fuel capacity at maximum payload, 1,200 pounds. Maximum takeoff weight. 5,200 pounds zero fuel weight. Minus 4,400 pounds fuel allowed. 800 pounds. Assuming maximum payload, the only weight permitted in excess of the zero fuel weight must consist of usable fuel. In this case, 133.3 gallons, gal. 4. Calculate the payload at maximum fuel capacity, 180 gallons. Basic empty weight. 3,200 pounds maximum usable fuel. Plus 1,080 pounds weight with max fuel. 4,280 pounds maximum takeoff weight. 5,200 pounds weight with max fuel. Minus 4,280 pounds payload allowed. 920 pounds. Assuming maximum fuel, the payload is the difference between the weight of the fueled airplane and the maximum takeoff weight. Some multi-engine airplanes have a ramp weight, which is in excess of the maximum takeoff weight. The ramp weight is an allowance for fuel that would be burned during taxi and run-up, permitting a takeoff at full maximum takeoff weight. The airplane must weigh no more than maximum takeoff weight at the beginning of the takeoff roll. A maximum landing weight is a limitation against landing at a weight in excess of the published value. This requires pre-flight planning of fuel burn to ensure that the airplane weight upon arrival at destination is at or below the maximum landing weight. In the event of an emergency requiring an immediate landing, the pilot should recognize that the structural margins designed into the airplane are not fully available when over landing weight. An overweight landing inspection may be advisable. The service manual or manufacturer should be consulted. Although the foregoing problems only dealt with weight, the balance portion of weight and balance is equally vital. The flight characteristics of the multi-engine airplane vary significantly with shifts of the center of gravity, CG, within the approved envelope. Favorable stall characteristics. At aft CG, the airplane is less stable, with a slightly lower stalling speed, a slightly faster cruising speed, and less desirable stall characteristics. Forward CG limits are usually determined in certification by elevator/stabulator authority in the landing round out. Aft CG limits are determined by the minimum acceptable longitudinal stability. It is contrary to the airplane's operating limitations and 14 CFR to exceed any weight and balance parameter. Some multi-engine airplanes may require ballast to remain within CG limits under certain loading conditions. Several models require ballast in the aft baggage compartment with only a student and instructor on board to avoid exceeding the forward CG limit. When passengers are seated in the aftmost seats of some models, Ballast or baggage may be required in the nose baggage compartment to avoid exceeding the aft CG limit. The pilot must direct the seating of passengers and placement of baggage and cargo to achieve a CG within the approved envelope. Most multi-engine airplanes have general loading recommendations in the weight and balance section of the AFM/PO. When ballast is added, it must be securely tied down, and it must not exceed the maximum allowable floor loading. Some airplanes make use of a special weight and balance plotter. It consists of several movable parts that can be adjusted over a plotting board on which the CG envelope is printed. The reverse side of the typical plotter contains general loading recommendations for the particular airplane. A pencil line plot can be made directly on the CG envelope and printed on the working side of the plotting board. This plot can easily be erased and recalculated anew for each flight. This plotter is to be used only for the make and model airplane for which it was designed. Ground operation good habits learned with single-engine airplanes are directly applicable to multi-engine airplanes for pre-flight and engine start. Upon placing the airplane in motion to taxi, the new multi-engine pilot notices several differences, however. The most obvious is the increased wingspan and the need for even greater vigilance while taxiing in close quarters. Ground handling may seem somewhat ponderous and the multi-engine airplane is not as nimble as the typical 2- or 4-place single-engine airplane. As always, use care not to ride the brakes by keeping engine power to a minimum. One ground handling advantage of the multi-engine airplane over single-engine airplanes is the differential power capability. Turning with an assist from differential power minimizes both the need for brakes during turns and the turning radius. At forward CG, the airplane is more stable, with a slightly higher stalling speed, a slightly slower cruising speed, and the pilot should be aware, however, that making a sharp turn assisted by brakes and differential power can cause the 12-to-12 airplane to pivot about a stationary inboard wheel in landing gear. This is abuse for which the airplane was not designed and should be guarded against. Unless otherwise directed by the AFM/PO, all ground operations should be conducted with the cowl flaps fully open. The use of strobe lights is normally deferred until taxiing onto the active runway. Matched in their normal ranges. A directed and purposeful scan of the engine gauges can be accomplished well before the airplane approaches rotation speed. If a crosswind is present, the aileron displacement in the direction of the crosswind may be reduced as the airplane accelerates. The elevator/stabilator control should be held neutral throughout. Normal and crosswind takeoff and climb with the before takeoff checklist, which includes a pre-takeoff safety brief complete and air traffic control, ATC, clearance received. The airplane should be taxied into position on the runway center line. If departing from an airport without an operating control tower, a careful check for approaching aircraft should be made along with a radio advisory on the appropriate frequency. Sharp turns onto the runway combined with a rolling takeoff are not a good operating practice and may be prohibited by the AFM/PO due to the possibility of unporting a fuel tank pickup. The takeoff itself may be prohibited by the AFM/PO under any circumstances below certain fuel levels. The flight controls should be positioned for a crosswind, if present. Exterior lights, such as landing and taxi lights, and wingtip strobes should be illuminated immediately prior to initiating the takeoff roll, day or night. If holding in takeoff position for any length of time, particularly at night, the pilot should activate all exterior lights upon taxiing into position. Takeoff power should be set as recommended in the AFM/PO. With normally aspirated, non-turbocharged engines, this is full throttle. Full throttle is also used in most turbocharged engines. There are some turbocharged engines, however, that require the pilot to set a specific power setting, usually just below redline manifold pressure. This yields takeoff power with less than full throttle travel. Turbocharged engines often require special consideration. Throttle motion with turbocharged engines should be exceptionally smooth and deliberate. It is acceptable, and may even be desirable, to hold the airplane in position with brakes as the throttles are advanced. Brake release customarily occurs after significant boost from the turbocharger is established. This prevents wasting runway with slow, partial throttle acceleration as the engine power is increased. If runway length or obstacle clearance is critical, full power should be set before brake release as specified in the performance charts. As takeoff power is established, initial attention should be divided between tracking the runway centerline and monitoring the engine gauges. Many novice multi-engine pilots tend to fixate on the airspeed indicator just as soon as the airplane begins its takeoff roll. Instead, The pilot should confirm that both engines are developing full rated manifold pressure and RPM, and that is the fuel flows, fuel pressures, exhaust gas temperatures, EGTs, and oil pressures are. Full rated takeoff power should be used for every takeoff. Partial power takeoffs are not recommended. There is no evidence to suggest that the life of modern reciprocating engines is prolonged by partial power takeoffs. Paradoxically, excessive heat and engine wear can occur with partial power as the fuel metering system fails to deliver the slightly over-rich mixture vital for engine cooling during takeoff. There are several key airspeeds to be noted during the takeoff and climb sequence in any twin. The first speed to consider is VMC. If an engine fails below VMC while the airplane is on the ground, the takeoff must be rejected. Directional control can only be maintained by promptly closing both throttles and using rudder and brakes as required. If an engine fails below VMC while airborne, directional control is not possible with the remaining engine producing takeoff power. On takeoffs, therefore, the airplane should never be airborne before the airspeed reaches and exceeds VMC. Pilots should use the manufacturer's recommended rotation speed, VR, or liftoff speed, VLOF. If no such speeds are published, a minimum of VMC plus 5 knots should be used for VR. The rotation to a takeoff pitch attitude is performed with smooth control inputs. With a crosswind, the pilot should ensure that the landing gear does not momentarily touch the runway after the airplane has lifted off, as a side drift is present. The rotation may be accomplished more positively and or at a higher speed under these conditions. However, the pilot should keep in mind that the AFM/PO performance figures for accelerate stop distance, takeoff ground roll, and distance to clear an obstacle were calculated at the recommended VR and or VLOF speed. After liftoff, the next consideration is to gain altitude as rapidly as possible. To assist the pilot in takeoff and initial climb profile, some AFM/POs give a 50-foot or 50-foot barrier speed to use as a target during rotation, liftoff, and acceleration to VY. Prior to takeoff, pilots should review the takeoff distance to 50 feet above ground level, AGL, and the stopping distance from 50 feet AGL and add the distance together. If the runway is no longer than the total value, the odds are very good that if anything fails, it will be an off-runway landing at the least. After leaving the ground, altitude gain is more important than achieving an excessive airspeed. Experience has shown that excessive speed cannot be effectively converted into altitude in the event 12 to 13 of an engine failure. Additional altitude increases the time available to recognize and respond to any aircraft abnormality or emergency during the climb segment. Excessive climb attitudes can be just as dangerous as excessive airspeed. Steep climb attitudes limit forward visibility and impede the pilot's ability to detect and avoid other traffic. The airplane should be allowed to accelerate in a shallow climb to attain VY, the best all-engine rate of climb speed. VY should then be maintained until a safe single-engine maneuvering altitude, considering terrain and obstructions, is achieved. Any speed above or below VY reduces the performance of the airplane. Even with all engines operating normally, terrain and obstruction clearance during the initial climb after takeoff is an important pre-flight consideration. Most airliners and most turbine-powered airplanes climb out at an attitude that yields best rate of climb, VY, usually utilizing a flight management system, FMS. When to raise the landing gear after takeoff depends on several factors. Normally, the gear should be retracted when there is insufficient runway available for landing and after a positive rate of climb is established as indicated on the altimeter. If an excessive amount of runway is available, it would not be prudent to leave the landing gear down for an extended period of time and sacrifice climb performance and acceleration. Leaving the gear extended after the point at which a landing cannot be accomplished on the runway is a hazard. In some multi-engine airplanes, operating in a high-density altitude environment, a positive rate of climb with the landing gear down is not possible. Waiting for a positive rate of climb under these conditions is not practicable. An important point to remember is that raising the landing gear as early as possible after liftoff drastically decreases the drag profile and significantly increases climb performance should an engine failure occur. An equally important point to remember is that leaving the gear down to land on sufficient runway or overrun is a much better option than landing with the gear retracted. A general recommendation is to raise the landing gear not later than vice airspeed, and once the gear is up, consider it a go commitment if climb performance is available. Some AFM/POs direct the pilot to apply the wheel brakes momentarily after liftoff to stop wheel rotation prior to landing gear retraction. If flaps were extended for takeoff, they should be retracted as recommended in the AFM/PO. Once a safe, single-engine maneuvering altitude has been reached, typically a minimum of 400-500 feet AGL, the transition to an en route climb speed should be made. This speed is higher than VY and is usually maintained to cruising altitude. En route climb speed gives better visibility, increased engine cooling, and a higher ground speed. Takeoff power can be reduced, if desired, as the transition to en route climb speed is made. Some airplanes have a climb power setting published in the AFM/PO as a recommendation, or sometimes as a limitation, which should then be set for en route climb. If there is no climb power setting published, it is customary, but not a requirement, to reduce manifold pressure and RPM somewhat for en route climb. The propellers are usually synchronized after the first power reduction and the yaw damper, if installed, engaged. The AFM/PO may also recommend leaning the mixtures during climb. The climb checklist should be accomplished as traffic and workload allow. Figure 12.7. Level off and cruise. Upon leveling off at cruising altitude, the pilot should allow the airplane to accelerate at climb power until cruising airspeed is achieved, and then cruise power and RPM should be set. To extract the maximum cruise performance from any airplane, the power setting tables provided by the manufacturer should be closely followed. If the cylinder head and oil temperatures are within their normal ranges, the cowl flaps may be closed. When the engine temperatures have stabilized, the mixtures may be leaned per AFM/PO recommendations. The remainder of the cruise checklist should be completed by this point. Fuel management in multi-engine airplanes is often more complex than in single-engine airplanes. Depending upon system design, the pilot may need to select between main tanks and auxiliary tanks or even employ fuel transfer from one tank to another. In complex fuel systems, limitations are often found restricting the use of some tanks to level flight only or requiring a reserve of fuel in the main tanks for descent and landing. Electric fuel pump operation can vary widely among different models also, particularly during tank switching or fuel transfer. Some fuel pumps are to be on for takeoff and landing, others are to be off. There is simply no substitute for thorough systems and AFM/PO knowledge when operating complex aircraft. Normal approach and landing. Given the higher cruising speed, and frequently altitude, of multi-engine airplanes over most single-engine airplanes, the descent must be planned in advance. A hurried, last-minute descent with power at or near idle is inefficient and can cause excessive engine cooling. It may also lead to passenger discomfort, particularly if the airplane is unpressurized. As a rule of thumb, if terrain and passenger conditions permit, a maximum of a 500 fpm rate of descent should be planned. Pressurized airplanes can plan for higher descent rates, if desired. 12 to 14. 500 feet 1. Accelerate to cruise. Climb 2. Set climb power 3. Climb checklist. 3. Positive rate. Gear up. Climb at VY. 2. Lift off. Published VR or VLOF. If not published, VMC plus 5 knots. 1. 1. 8. Figure 12.7. Takeoff and climb profile. In a descent, some airplanes require a minimum EGT or may have a minimum power setting or cylinder head temperature to observe. In any case, combinations of very low manifold pressure and high RPM settings are strongly discouraged by engine manufacturers. If higher descent rates are necessary, the pilot should consider extending partial flaps or lowering the landing gear before retarding the power excessively. The descent checklist should be initiated upon leaving cruising altitude and completed before arrival in the terminal area. Upon arrival in the terminal area, pilots are encouraged to turn on their landing and recognition lights when operating below 10,000 feet, day or night, and especially when operating within 10 miles of any airport or in conditions of reduced visibility. The traffic pattern and approach are typically flown at somewhat higher indicated airspeeds in a multi-engine airplane contrasted to most single-engine airplanes. The pilot may allow for this through an early start on the before landing checklist. This provides time for proper planning, spacing, and thinking well ahead of the airplane. Many multi-engine airplanes have partial flap extension speeds above VFE, and partial flaps can be deployed prior to traffic pattern entry. Normally, the landing gear should be selected and confirmed down when abeam the intended point of landing as the downwind leg is flown. Figure 12.8. The FAA recommends a stabilized approach concept. To the greatest extent practical, on final approach and within 500 feet AGL, the airplane should be on speed, in trim, configured for landing, tracking the extended centerline of the runway, and established in a constant angle of descent towards an aim point in the touchdown zone. Absent unusual flight conditions, only minor corrections are required to maintain this approach to the roundout and touchdown. The final approach should be made with power and at a speed recommended by the manufacturer. If a recommended speed is not furnished, the speed should be no slower than the single-engine best rate of climb speed, (VYSE), until short final with the landing assured, but in no case less than critical engine out minimum control speed, (VMC). Some multi-engine pilots prefer to delay full flap extension to short final with the landing assured. This is an acceptable technique with appropriate experience and familiarity with the airplane. In the roundout for landing, residual power is gradually reduced to idle. With the higher wing loading of multi-engine airplanes and with the drag from two windmilling propellers, there is minimal float. Full stall landings are generally undesirable in twins. The airplane should be held off as with the high-performance single-engine model, allowing touchdown of the main wheels prior to a full stall. Under favorable wind and runway conditions, the nose wheel can be held off for best aerodynamic braking. Even as the nose wheel is gently lowered to the runway centerline, continued elevator back pressure greatly assists the wheel brakes in stopping the airplane. 12 to 15. 1. Approaching traffic pattern 1. Descent checklist 2. Reduced to traffic pattern airspeed and altitude. Final 1. Gear check down 2. Flaps landing position. 4. 5. Airspeed 1.3 SO or manufacturer's recommended. Figure 12.8. Normal 2-engine approach and landing. If runway length is critical, or with a strong crosswind, or if the surface is contaminated with water, ice or snow, it is undesirable to rely solely on aerodynamic braking after touchdown. The full weight of the airplane should be placed on the wheels as soon as practicable. The wheel brakes are more effective than aerodynamic braking alone in decelerating the airplane. Once on the ground, elevator back pressure should be used to place additional weight on the main wheels and to add additional drag. When necessary, wing flap retraction also adds additional weight to the wheels and improves braking effectivity. Flap retraction during the landing rollout is discouraged, however, unless there is a clear, operational need. It should not be accomplished as routine with each landing. Some multi-engine airplanes, particularly those of the cabin class variety, can be flown through the roundout and touchdown with a small amount of power. This is an acceptable technique to prevent high sink rates and to cushion the touchdown. The pilot should keep in mind, however, that the primary purpose in landing is to get the airplane down and stopped. This technique should only be attempted when there is a generous margin of runway length. As propeller blast flows directly over the wings, lift as well as thrust is produced. The pilot should taxi clear of the runway as soon as speed and safety permit, and then accomplish the after-landing checklist. Ordinarily, no attempt should be made to retract the wing flaps or perform other checklist duties. 12 to 16. Downwind 1. Flaps approach position 2. Gear down 3. Before landing checklist. 2. Base leg 1. Gear check down 2. Check for conflicting traffic. 3. Until the airplane has been brought to a halt when clear of the active runway. Exceptions to this would be the rare operational needs discussed above, to relieve the weight from the wings and place it on the wheels. In these cases, AFM/PO guidance should be followed. The pilot should not indiscriminately reach out for any switch or control on landing rollout. An inadvertent landing gear retraction while meaning to retract the wing flaps may result. Crosswind approach and landing. The multi-engine airplane is often easier to land in a crosswind than a single-engine airplane due to its higher approach and landing speed. In any event, the principles are no different between singles and twins. Prior to touchdown, the longitudinal axis must be aligned with the runway centerline to avoid landing gear side loads. The two primary methods, crab and wing low, are typically used in conjunction with each other. As soon as the airplane rolls out onto final approach, the crab angle to track the extended runway centerline is established. This is coordinated flight with adjustments to heading to compensate for wind drift either left or right. Prior to touchdown, the transition to a side slip is made with the upwind wing lowered and opposite rudder applied to prevent a turn. The airplane touches down on the landing gear of the upwind wing first, followed by that of the downwind wing, and then the nose gear. Follow through with the flight controls involves in increasing application of aileron into the wind until full control deflection is reached. The point at which the transition from the crab to the side slip is made is dependent upon pilot familiarity with the airplane and experience. With high skill and experience levels, the transition can be made during the roundout just before touchdown. With lesser skill and experience levels, the transition is made at increasing distances from the runway. Some multi-engine airplanes, as some single-engine airplanes, have AFM/PO limitations against slips in excess of a certain time period, 30 seconds, for example. This is to prevent engine power loss from fuel starvation as the fuel in the tank of the lowered wing flows towards the wingtip, away from the fuel pickup point. This time limit must be observed if the wing low method is utilized. Some multi-engine pilots prefer to use differential power to assist in crosswind landings. The asymmetrical thrust produces a yawing moment little different from that produced by the rudder. When the upwind wing is lowered, power on the upwind engine is increased to prevent the airplane from turning. This alternate technique is completely acceptable, but most pilots feel they can react to changing wind conditions quicker with rudder and aileron than throttle movement. This is especially true with turbocharged engines where the throttle response may lag momentarily. The differential power technique should be practiced with an instructor before being attempted alone. Short field takeoff and climb. The short field takeoff and climb differs from the normal takeoff and climb in the airspeeds and initial climb profile. Some AFM/POs give separate short field takeoff procedures and performance charts that recommend specific flap settings and airspeeds. Other AFM/POs do not provide separate short field procedures. In the absence of such specific procedures, the airplane should be operated only as recommended in the AFM/PO. No operations should be conducted contrary to the recommendations in the AFM/PO. On short field takeoffs in general, just after rotation and liftoff, the airplane should be allowed to accelerate to VX, making the initial climb over obstacles at VX and transitioning to VY as obstacles are cleared. Figure 12.9. When partial flaps are recommended for short field takeoffs, many light twins have a strong tendency to become airborne prior to VMC plus 5 knots. Attempting to prevent premature liftoff with forward elevator pressure results in wheel barrowing. To prevent this, allow the airplane to become airborne, but only a few inches above the runway. The pilot should be prepared to promptly abort the takeoff and land in the event of engine failure on takeoff with landing gear and flaps extended at airspeeds below VX. Engine failure on takeoff, particularly with obstructions, is compounded by the low airspeeds and steep climb attitudes utilized in short field takeoffs. VX and VXSC are often perilously close to VMC, leaving scant margin for error in the event of engine failure as VXSC is assumed. If flaps were used for takeoff, the engine failure situation becomes even more critical due to the additional drag incurred. If VX is less than 5 knots higher than VMC, give strong consideration to reducing useful load or using another runway in order to increase the takeoff margins so that a short field technique is not required. Short field approach and landing. The primary elements of a short field approach and landing do not differ significantly from a normal approach and landing. Many manufacturers do not publish short field landing techniques or performance charts in the AFM/PO. In the absence of specific short field approach and landing procedures, the airplane should be operated as recommended in the AFM/PO. No operations should be conducted contrary to the AFM/PO recommendations. The emphasis in a short field approach is on configuration, full flaps, a stabilized approach with a constant angle of descent, and precise airspeed control. As part of a short VY 50 feet, VY 12 to 17. Figure 12.9. Short field takeoff and climb. Field approach and landing procedure. Some AFM/POs recommend a slightly slower than normal approach airspeed. If no such slower speed is published, use the AFM/PO recommended normal approach speed. Full flaps are used to provide the steepest approach angle. If obstacles are present, the approach should be planned so that no drastic power reductions are required after they are cleared. The power should be smoothly reduced to idle in the roundout prior to touchdown. Pilots should keep in mind that the propeller blast blows over the wings, providing some lift in addition to thrust. Reducing power significantly, just after obstacle clearance, usually results in a sudden, high sink rate that may lead to a hard landing. After the short field touchdown, maximum stopping effort is achieved by retracting the wing flaps, adding back pressure to the elevator/stabilator, and applying heavy braking. However, if the runway length permits, The wing flaps should be left in the extended position until the airplane has been stopped clear of the runway. There is always a significant risk of retracting the landing gear instead of the wing flaps when flap retraction is attempted on the landing rollout. Landing conditions that involve a short field, high winds, or strong crosswinds are just about the only situations where flap retraction on the landing rollout should be considered. When there is an operational need to retract the flaps just after touchdown, it must be done deliberately with the flap handle positively identified before it is moved. Go around. When the decision to go around is made, the throttles should be advanced to takeoff power. With adequate airspeed, the airplane should be placed in a climb pitch attitude. These actions, which are accomplished simultaneously, arrest the sink rate and place the airplane in the proper attitude for transition to a climb. The initial target airspeed is Vy or Vx if obstructions are present. With sufficient airspeed, the flaps should be retracted from full to an intermediate position and the landing gear retracted when there is a positive rate of climb and no chance of runway contact. The remaining flaps should then be retracted. Figure 12.10. If the go-round was initiated due to conflicting traffic on the ground or aloft, the pilot should maneuver to the side so as to keep the conflicting traffic in sight. This may involve a shallow bank turn to offset and then parallel the runway/landing area. If the airplane was in trim for the landing approach when the go-around was commenced, it soon requires a great deal of forward elevator/stabilator pressure as the airplane accelerates away in a climb. The pilot should apply appropriate forward pressure to maintain the desired pitch attitude. Trim should be commenced immediately. The balked landing checklist should be reviewed as workload permits. Flaps should be retracted before the landing gear for two reasons. First, on most airplanes, full flaps produce more drag than the extended landing gear. Secondly, the airplane tends to settle somewhat with flap retraction, and the landing gear should be down in the event of an inadvertent, momentary touchdown. Many multi-engine airplanes have a landing gear retraction speed significantly less than the extension speed. Care should be exercised during the go-around not to exceed the retraction speed. If the pilot desires to return for a landing, it is essential to re-accomplish the entire before landing checklist. An interruption to a pilot's habit patterns, such as a go-around, is a classic scenario for a subsequent gear-up landing. The preceding discussion about doing a go-around assumes that the maneuver was initiated from normal approach speeds or faster. If the go-around was initiated from a low airspeed, the initial pitch up to a climb attitude must be tempered with the necessity of maintaining adequate flying speed throughout the maneuver. Examples of where this applies include a go-around initiated from the landing roundout or recovery. Positive rate of climb, retract. Gear, climb. At Vy. Retract remaining. Flaps. 500. Cruise climb. Timely decision to make go-around. Apply max power, adjust pitch attitude to arrest sink rate. Flaps 2. Intermediate. Figure 12.10. Go-around procedure. 12 to 18. From a bad bounce, as well as a go-around initiated due to an inadvertent approach to a stall. The first priority is always to maintain control and obtain adequate flying speed. A few moments of level or near-level flight may be required as the airplane accelerates up to climb speed. Rejected takeoff. A takeoff can be rejected for the same reasons a takeoff in a single-engine airplane would be rejected. Once the decision to reject a takeoff is made, the pilot should promptly close both throttles and maintain directional control with the rudder, nose wheel steering, and brakes. Aggressive use of rudder, nose wheel steering, and brakes may be required to keep the airplane on the runway. Particularly, if an engine failure is not immediately recognized and accompanied by prompt closure of both throttles. However, the primary objective is not necessarily to stop the airplane in the shortest distance, but to maintain control of the airplane as it decelerates. In some situations, it may be preferable to continue into the overrun area under control, rather than risk directional control loss, landing gear collapse, or tire/brake failure in an attempt to stop the airplane in the shortest possible distance. Engine failure after liftoff. A takeoff or go-around is the most critical time to suffer an engine failure. The airplane will be slow, close to the ground, and may even have landing gear and flaps extended. Altitude and time is minimal. Until feathered, the propeller of the failed engine is windmilling, producing a great deal of drag and yawing tendency. Airplane climb performance is marginal or even non-existent, and obstructions may lie ahead. An emergency contingency plan and safety brief should be clearly understood well before the takeoff roll commences. An engine failure before a predetermined airspeed or point results in an aborted takeoff. An engine failure after a certain airspeed and point, with the gear up, and climb performance assured result in a continued takeoff. With loss of an engine, it is paramount to maintain airplane control and comply with the manufacturer's recommended emergency procedures. Complete failure of one engine shortly after takeoff can be broadly categorized into one of three following scenarios. Landing gear down. If the engine failure occurs prior to selecting the landing gear to the up position, Figure 12.11, keep the nose as straight as possible, close both throttles, allow the nose to maintain airspeed and descend to the runway. Concentrate on a normal landing and do not force the aircraft on the ground. Land on the remaining runway or overrun. Depending upon how quickly the pilot reacts to the sudden yaw, the airplane may run off the side of the runway by the time action is taken. There are really no other practical options. As discussed earlier, the chances of maintaining directional control while retracting the flaps, if extended, landing gear, feathering the propeller, and accelerating are minimal. On some airplanes with a single engine-driven hydraulic pump, failure of that engine means the only way to raise the landing gear is to allow the engine to windmill or to use a hand pump. This is not a viable alternative during takeoff. 1. 8. 1. If engine failure occurs at or before liftoff, abort the takeoff. If failure of engine occurs after liftoff, 1. Maintain directional control. 2. Close both throttles. 2. Figure 12.11. Engine failure on takeoff, landing gear down. 12-19. Engine failure. Liftoff. Descend advice. Land under control on or off runway. Overrun area. Figure 12.12. Engine failure on takeoff, inadequate climb performance. Landing gear control selected up, single engine climb performance inadequate when operating near or above the single engine ceiling and an engine failure is experienced shortly after liftoff. A landing must be accomplished on whatever essentially lies ahead. Figure 12.12, there is also the option of continuing ahead, in a descent advice with the remaining engine producing power, as long as the pilot is not tempted to remain airborne beyond the airplane's performance capability. Remaining airborne and bleeding off airspeed in a futile attempt to maintain altitude is almost invariably fatal. Landing under control is paramount. The greatest hazard in a single-engine takeoff is attempting to fly when it is not within the performance capability of the airplane to do so. An accident is inevitable. Analysis of engine failures on takeoff reveals a very high success rate of off-airport engine inoperative landings when the airplane is landed under control. Analysis also reveals a very high fatality rate in stall spin accidents when the pilot attempts flight beyond the performance capability of the airplane. As mentioned previously, if the airplane's landing gear retraction mechanism is dependent upon hydraulic pressure from a certain engine-driven pump, failure of that engine can mean a loss of hundreds of feet of altitude as the pilot either windmills the engine to provide hydraulic pressure to raise the gear or raises it manually with a backup pump. Landing gear control selected up, single engine climb performance adequate. If the single engine rate of climb is adequate, the procedures for continued flight should be followed. Figure 12.13. There are 4 areas of concern: control, configuration, climb, and checklist. Control. The first consideration following engine failure during takeoff is to maintain control of the airplane. Maintaining directional control with prompt and often aggressive rudder application and stopping the yaw is critical to the safety of flight. Ensure that airspeed stays above VMC. If the yaw cannot be controlled with full rudder applied, reducing thrust on the obstruction clearance altitude or above. 1. If failure of engine occurs after liftoff, 1. Maintain directional control vice, heading, bank into operating engine. 2. Power increase or set for takeoff. 3. Drag reduce, gear, flaps. 4. Identify inoperative engine. 5. Verify inoperative engine. 6. Feather inoperative engine. 2. 3. At 500 or obstruction clearance altitude. 7. Engine failure checklist. Circle and land. Figure 12.13. Landing gear up, adequate climb performance. 12-20. Operative engine is the only alternative. Attempting to correct the roll with aileron without first applying rudder increases drag and adverse yaw and further degrades directional control. After rudder is applied to stop the yaw, A slight amount of aileron should be used to bank the airplane toward the operative engine. This is the most efficient way to control the aircraft, minimize drag, and gain the most performance. Control forces, particularly on the rudder, may be high. The pitch attitude for vice has to be lowered from that of VY. At least 5 degrees of bank should be used initially to stop the yaw and maintain directional control. This initial bank input is held only momentarily, just long enough to establish or ensure directional control. Climb performance suffers when bank angles exceed approximately 2 or 3 degrees, but obtaining and maintaining vice and directional control are paramount. Trim should be adjusted to lower the control forces. Configuration: the memory items from the engine failure after takeoff checklist should be promptly executed to configure the airplane for climb. Figure 1214. The specific procedures to follow are found in the AFM/PO and checklist for the particular airplane. Most direct the pilot to assume vice, set takeoff power, retract the flaps and landing gear, identify, verify, and feather the failed engine. On some airplanes, the landing gear is to be retracted before the flaps. When the suspected throttle is retarded is verification that the correct engine has been identified as failed. The corresponding propeller control should be brought fully aft to feather the engine. Climb: as soon as directional control is established and the airplane configured for climb, the bank angle should be reduced to that producing best climb performance. Without specific guidance for zero side slip, a bank of 2 degrees and 1/3 to 1/2 ball deflection on the slip/skid indicator is suggested. Vice is maintained with pitch control. As turning flight reduces climb performance, climb should be made straight ahead or with shallow turns to avoid obstacles to an altitude of at least 400 feet AGL before attempting a return to the airport. Checklist: having accomplished the memory items from the engine failure after takeoff checklist, the printed copy should be reviewed as time permits. The securing failed engine checklist should then be accomplished. Figure 1215. Unless the pilot suspects an engine fire, the remaining items should be accomplished deliberately and without undue haste. Airplane control should never be sacrificed to execute the remaining checklists. The priority items have already been accomplished from memory. The identify step is for the pilot to initially identify the failed engine. Confirmation on the engine gauges may or may not be possible, depending upon the failure mode. Identification should be primarily through the control inputs required to maintain straight flight, not the engine gauges. The verify step directs the pilot to retard the throttle of the engine thought to have failed. No change in performance. Other than closing the cowl flap of the failed engine, none of these items, if left undone, adversely affects airplane climb performance. There is a distinct possibility of actuating an incorrect switch or control if the procedure is rushed. The pilot should concentrate on flying the airplane and extracting maximum performance. If an ATC facility is available, an emergency should be declared. Engine failure after takeoff. Airspeed: maintain vice mixtures, rich propellers. High RPM throttles, full power flaps, up landing gear. Up identify, determine failed engine verify, close throttle of failed engine propeller. Feather trim tabs. Adjust failed engine. Secure as soon as practical. Land bold-faced items require immediate action and are to be accomplished from memory. Figure 12-14. Typical engine failure after takeoff emergency checklist. The memory items in the engine failure after takeoff checklist may be redundant with the airplane's existing configuration. For example, in the third takeoff scenario, the gear and flaps were assumed to already be retracted, yet the memory items included gear and flaps. This is not an oversight. The purpose of the memory items is to either initiate the appropriate action or to confirm that a condition exists. Action on each item may not be required in all cases. The memory items also apply to more than one circumstance. In an engine failure from a go-around, for example, the landing gear and flaps would likely be extended when the failure occurred. The 3 preceding takeoff scenarios all include the landing gear as a key element in the decision to land or continue. With the landing gear selector in the down position, for example, continued takeoff and climb is not recommended. This situation, however, is not justification to retract the 12-21. Securing failed engine. Mixture: idle cutoff magnetos, off alternator. Off cowl flap, close boost pump, off fuel selector. Off prop sink, off electrical load, reduce crossfeed. Consider. Figure 1215. Typical securing failed engine emergency checklist. Landing gear the moment the airplane lifts off the surface on takeoff is a normal procedure. The landing gear should remain selected down as long as there is usable runway or overrun available to land on. The use of wing flaps for takeoff virtually eliminates the likelihood of a single-engine climb until the flaps are retracted. There are two time-tested memory aids the pilot may find useful in dealing with engine-out scenarios. The first, dead foot, dead engine, is used to assist in identifying the failed engine. Depending on the failure mode, the pilot will not be able to consistently identify the failed engine in a timely manner from the engine gauges. In maintaining directional control, however, rudder pressure is exerted on the side, left or right, of the airplane with the operating engine. Thus, the dead foot is on the same side as the dead engine. Variations on this saying include idle foot, idle engine, and working foot, working engine. The second memory aid has to do with climb performance. The phrase "raise the dead" is a reminder that the best climb performance is obtained with a very shallow bank, about 2 degrees toward the operating engine. Therefore, the inoperative, or dead engine should be raised with a very slight bank. Not all engine power losses are complete failures. Sometimes the failure mode is such that partial power may be available. If there is a performance loss when the throttle of the affected engine is retarded, the pilot should consider allowing it to run until altitude and airspeed permit safe single-engine flight, if this can be done without compromising safety. Attempts to save a malfunctioning engine can lead to a loss of the entire airplane. Engine failure during flight. Engine failures well above the ground are handled differently than those occurring at lower speeds and altitudes. Cruise airspeed allows better airplane control and altitude, which may permit time for a possible diagnosis and remedy of the failure. Maintaining airplane control, however, is still paramount. Airplanes have been lost at altitude due to apparent fixation on the engine problem to the detriment of flying the airplane. Not all engine failures or malfunctions are catastrophic in nature, catastrophic meaning a major mechanical failure that damages the engine and precludes further engine operation. Many cases of power loss are related to fuel starvation, where restoration of power may be made with the selection of another tank. An orderly inventory of gauges and switches may reveal the problem. Carburetor heat or alternate air can be selected. The affected engine may run smoothly on just one magneto or at a lower power setting. Altering the mixture may help. If fuel vapor formation is suspected, fuel boost pump operation may be used to eliminate flow and pressure fluctuations. Although it is a natural desire among pilots to save an ailing engine with a precautionary shutdown, the engine should be left running if there is any doubt as to needing it for further safe flight. Catastrophic failure accompanied by heavy vibration, smoke, blistering paint, or large trails of oil, on the other hand, indicate a critical situation. The affected engine should be feathered and the securing failed engine checklist completed. The pilot should divert to the nearest suitable airport and declare an emergency with ATC for priority handling. Fuel cross-feed is a method of getting fuel from a tank on one side of the airplane to an operating engine on the other. Cross-feed is used for extended single-engine operation. If a suitable airport is close at hand, there is no need to consider cross-feed. If prolonged flight on a single engine is inevitable due to airport non-availability, then cross-feed allows use of fuel that would otherwise be unavailable to the operating engine. It also permits the pilot to balance the fuel consumption to avoid an out-of-balance wing heaviness. The AFM/PO procedures for cross-feed vary widely. Thorough fuel system knowledge is essential if cross-feed is to be conducted. Fuel selector positions and fuel boost pump usage for cross-feed differ greatly among multi-engine airplanes. Prior to landing, cross-feed should be terminated and the operating engine returned to its main tank fuel supply. If the airplane is above its single-engine absolute ceiling at the time of engine failure, it slowly loses altitude. The pilot should maintain VICE to minimize the rate of altitude loss. This drift-down rate is greatest immediately following the failure and decreases as the single-engine ceiling is approached. Due to performance variations caused by engine and propeller wear, turbulence, and pilot technique. 12 to 22. The airplane may not maintain altitude even at its published single-engine ceiling. Any further rate of sink, however, would likely be modest. An engine failure in a descent or other low-power setting can be deceiving. The dramatic yaw and performance loss is absent. At very low power settings, the pilot may not even be aware of a failure. If a failure is suspected, the pilot should advance both engine mixtures, propellers, and throttles significantly, to the takeoff settings if necessary, to correctly identify the failed engine. The power on the operative engine can always be reduced later. Engine inoperative approach and landing. The approach and landing with OA is essentially the same as a two-engine approach and landing. The traffic pattern should be flown at similar altitudes, airspeeds, and key positions as a two-engine approach. The differences are the reduced power available and the fact that the remaining thrust is asymmetrical. A higher than normal power setting is necessary on the operative engine. With adequate airspeed and performance, the landing gear can still be extended on the downwind leg, in which case it should be confirmed down no later than abeam the intended point of landing. Performance permitting, initial extension of wing flaps, typically 10 degrees, and a descent from pattern altitude can also be initiated on the downwind leg. The airspeed should be no slower than vice. The direction of the traffic pattern, and therefore the turns, is of no consequence as far as airplane controllability and performance are concerned. It is perfectly acceptable to make turns toward the failed engine. On the base leg, if performance is adequate, the flaps may be extended to an intermediate setting, typically 25 degrees. If the performance is inadequate, as measured by decay in airspeed or high sink rate, delay further flap extension until closer to the runway. Vice is still the minimum airspeed to maintain. On final approach, a normal, 3 degrees glide path to a landing is desirable. Visual approach slope indicator, VASI, or other vertical path lighting aids should be utilized if available. Slightly steeper approaches may be acceptable. However, a long, flat, low approach should be avoided. Large, sudden power applications or reductions should also be avoided. Maintain vice until the landing is assured, then slow to 1.3 VSO or the AFM/PO recommended speed. The final flap setting may be delayed until the landing is assured or the airplane may be landed with partial flaps. The airplane should remain in trim throughout. The pilot must be prepared, however, for a rudder trim change as the power of the operating engine is reduced to idle in the round out just prior to touchdown. With drag from only one windmilling propeller, the airplane tends to float more than on a two-engine approach. Precise airspeed control therefore is essential, especially when landing on a short, wet, and/or slippery surface. Some pilots favor resetting the rudder trim to neutral on final and compensating for yaw by holding rudder pressure for the remainder of the approach. This eliminates the rudder trim change close to the ground as the throttle is closed during the round out for landing. This technique eliminates the need for groping for the rudder trim and manipulating it to neutral during final approach, which many pilots find to be highly distracting. AFM/PO recommendations or personal preference should be used. A single-engine go-around must be avoided. As a practical matter in single-engine approaches, once the airplane is on final approach with landing gear and flaps extended, it is committed to land on the intended runway, on another runway, a taxiway, or grassy infield. The light twin does not have the performance to climb on one engine with landing gear and flaps extended. Considerable altitude is lost while maintaining vice and retracting landing gear and flaps. Losses of 500 feet or more are not unusual. If the landing gear has been lowered with an alternate means of extension, retraction may not be possible, virtually negating any climb capability. Engine inoperative flight principles. Best single-engine climb performance is obtained at vice with maximum available power and minimum drag. After the flaps and landing gear have been retracted and the propeller of the failed engine feathered, a key element in best climb performance is minimizing side slip. With a single-engine airplane or a multi-engine airplane with both engines operative, side slip is eliminated when the ball of the turn-and-bank instrument is centered. This is a condition of zero side slip, and the airplane is presenting its smallest possible profile to the relative wind. As a result, drag is at its minimum. Pilots know this as coordinated flight. In a multi-engine airplane with an inoperative engine, the centered ball is no longer the indicator of zero side slip due to asymmetrical thrust. In fact, there is no instrument at all that directly tells the pilot the flight conditions for zero side slip. In the absence of a yaw string, minimizing side slip is a matter of placing the airplane at a predetermined bank angle and ball position. The AFM/PO performance charts for single-engine flight were determined at zero side slip. If this performance is even to be approximated, the zero side slip technique must be utilized. 12 to 23. There are two different control inputs that can be used to counteract the asymmetrical thrust of a failed engine. 1. Yaw from the rudder. 2. The horizontal component of lift that results from bank. With the ailerons used individually, neither is correct. Used together in the proper combination, zero side slip and best climb performance are achieved. 3 different scenarios of airplane control inputs are presented below. Neither of the first two is correct. They are presented to illustrate the reasons for the zero side slip approach to best climb performance. 1. Engine in operative flight with wings level and ball centered requires large rudder input towards the operative engine. Figure 12 to 16, the result is a moderate side slip towards the inoperative engine. Climb performance is reduced by the moderate side slip. With wings level, VMC is significantly higher than published as there is no horizontal component of lift available to help the rudder combat asymmetrical thrust. 2. Engine in operative flight using ailerons alone requires an 8 to 10 degrees bank angle towards the operative engine. Figure 12 to 17, this assumes no rudder input. The ball is displaced well towards the operative engine. The result is a large side slip towards the operative engine. Climb performance is greatly reduced by the large side slip. 3. Rudder and ailerons used together in the proper combination result in a bank of approximately 2 degrees towards the operative engine. The ball is displaced approximately 1/3 to 1/2 towards the operative engine. The result is zero side slip and maximum climb performance. Figure 12 to 18, any attitude other than zero side slip increases drag, decreasing performance. VMC under these circumstances is higher than published, as less than the 5 degrees bank certification limit is employed. The precise condition of zero side slip, bank angle and ball position, varies slightly from model to model and with available power and airspeed. If the airplane is not equipped with counter-rotating propellers, it also varies slightly with the engine failed due to P-factor. The foregoing zero side slip recommendations apply to reciprocating engine multi-engine airplanes flown at vice with the inoperative engine feathered. The zero side slip ball position for straight flight is also the zero side slip position for turning flight. 12 to 24. R. E. L. A. T. I. V. E. W. I. N. D. Yaw string. Thrust. D. R. A. G. Slipstream. Fin effect due to side slip. Rudder force. Nav 1 108.00 113.00 Nav 2 108.00 110.60 WPT underscore 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 dis underscore 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 NMDTK underscore 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 degree TRK 360 degrees 134.000 118.000 com 1 123.800 118.000 com 2 130 120 110 1 109.90 80 70 TOS 106 KT 07 degrees Celsius 270 degrees 41 2 1 1 2 4,000 4,300 4,200 4,100 64,000 4,000 23,900 3,800 4,300 3,600 3,500 Wings level, ball centered, airplane slips toward dead engine. Results: high drag, large control surface deflections required, and rudder and fin in opposition due to side slip. XPDR 5537 IDNT LCL 3200. Temp 12 and 34 seconds. Alerts: 3400, 3300, 3100. Figure 12-16. Wings level engine out flight. When bank angle is plotted against climb performance for a hypothetical twin, zero side slip results in the best, however marginal, climb performance or the least rate of descent. Zero bank, all rudder to counteract yaw, degrades climb performance as a result of moderate side slip. Using bank angle alone, no rudder, severely degrades climb performance as a result of a large side slip. The actual bank angle for zero side slip varies among airplanes from 1 1/2 to 2 1/2 degrees. The position of the ball varies from 1/3 to 1/2 of a ball width from instrument center. D. Elated wing. R. Thrust. Yaw string. GARD. Nav 1 108.00 113.00 Nav 2 108.00 110.60 WPT underscore 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 dis underscore 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 NMDTK underscore 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 degree TRK 360 degrees 134.000 118.000 com 1 123.800 118.000 com 2 130 120 110 1 109.90 80 70 TOS 106 KT 07 degrees Celsius 270 degrees 4 1 2 1 1 2 4,000 4,300 4,200 4,100 64,000 4,000 23,900 3,800 4,300 3,600 3,500 Excess bank toward operating engine, no rudder input. Result, large side slip toward operating engine and greatly reduced climb performance. XPDR 5537 IDNT LCL 3200. 10, 12 and 34 seconds. Alerts. 3300. 3100. 3400. Figure 1217. Excessive bank engine outflight. For any multi-engine airplane, zero side slip can be confirmed through the use of a yaw string. A yaw string is a piece of string or yarn approximately 18 to 36 inches in length taped to the base of the windshield or to the nose near the windshield along the airplane center line. In two-engine coordinated flight, the relative wind causes the string to align itself with the longitudinal axis of the airplane, and it positions itself straight up the center of the windshield. This is zero side slip. Experimentation with slips and skids vividly displays the location of the relative wind. Adequate altitude and flying speed must be maintained while accomplishing these maneuvers. With an engine set to zero thrust, or feathered, and the airplane slow to vice, a climb with maximum power on. REA. L. TI. VEWND. I. Thrust. Yaw string. DRG. Rudder force. Nav 1 108.00 113.00 Nav 2 108.00 110.60 WPT underscore 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 dis underscore 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 NMDTK underscore 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 degree TRK 360 degrees 134.000 118.000 com 1 123.800 118.000 com 2 130 120 110 1 109.90 80 70 TOS 106 KT 07 degrees Celsius 270 degrees 4 1 2 1 1 2 4,000 4,300 4,200 4,100 64,000 4,000 23,900 3,800 4,300 3,600 3,500 Bank toward operating engine, no side slip. Results, much lower drag and smaller control surface deflections. XPDR 5537 IDNT LCL 3200. Alerts. 3300. 3100. 10, 12 and 34 seconds. 3400. Figure 1218. Zero side slip engine outflight. The remaining engine reveals the precise bank angle and ball deflection required for zero side slip and best climb performance. Zero side slip is again indicated by the yaw string when it aligns itself vertically on the windshield. There are very minor changes from this attitude depending upon the engine failed, with non-counter-rotating propellers, power available, airspeed and weight, but without more sensitive testing equipment, these changes are difficult to detect. The only significant difference would be the pitch attitude required to maintain vice under different density altitude, power available, and weight conditions. 12 to 25. If a yaw string is attached to the airplane at the time of a VMC demonstration, It is noted that VMC occurs under conditions of side slip. VMC was not determined under conditions of zero side slip during aircraft certification, and zero side slip is not part of a VMC demonstration for pilot certification. To review, there are two different sets of bank angles used in OA flight. 1. To maintain directional control of a multi-engine airplane suffering an engine failure at low speeds, such as climb, momentarily bank at least 5 degrees and a maximum of 10 degrees towards the operative engine as the pitch attitude for vice is set. This maneuver should be instinctive to the proficient multi-engine pilot and take only 1 to 2 seconds to attain. It is held just long enough to assure directional control as the pitch attitude for vice is assumed. 2. To obtain the best climb performance, the airplane must be flown at vice and zero side slip with the failed engine feathered and maximum available power from the operating engine. Zero side slip is approximately 2 degrees at bank toward the operating engine and a 1/3 to 1/2 ball deflection also toward the operating engine. The precise bank angle and ball position varies somewhat with make and model and power available. If above the airplane's single engine ceiling, this attitude and configuration results in the minimum rate of sink. In OA flight at low altitudes and airspeeds such as the initial climb after takeoff, pilots must operate the airplane so as to guard against the 3 major accident factors: 1. Loss of directional control, 2. Loss of performance, and 3. Loss of flying speed. All have equal potential to be lethal. Loss of flying speed is not a factor, however, when the airplane is operated with due regard for directional control and performance. Slow flight. There is nothing unusual about maneuvering during slow flight in a multi-engine airplane. Slow flight may be conducted in straight and level flight, turns, climbs, or descents. It can also be conducted in the clean configuration, landing configuration, or at any other combination of landing gear and flaps. Slow flight in a multi-engine airplane should be conducted so the maneuver can be completed no lower than 3,000 feet AGL or higher if recommended by the manufacturer. In all cases, practicing slow flight should be conducted at an adequate height above the ground for recovery should the airplane inadvertently stall. Pilots should closely monitor cylinder head and oil temperatures during slow flight. Some high performance. 12 to 26. Multi-engine airplanes tend to heat up fairly quickly under some conditions of slow flight, particularly in the landing configuration. Simulated engine failures should not be conducted during slow flight. The airplane will be well below VSSE and very close to VMC. Stability, stall warning, or stall avoidance devices should not be disabled while maneuvering during slow flight. Stall characteristics vary among multi-engine airplanes just as they do with single-engine airplanes, and therefore, a pilot must be familiar with them. Yet, the most important stall recovery step in a multi-engine airplane is the same as it is in all airplanes: reduce the angle of attack, AOA. For reference, the stall recovery procedure described in Chapter 4 is included in Figure 1219. Following a reduction in the OA and the stall warning being eliminated, the wings should be rolled level and power added as needed. Immediate full application of power in a stalled condition has an associated risk due to the possibility of asymmetric thrust. In addition, single-engine stalls or stalls with significantly more power on one engine than the other should not be attempted due to the likelihood of a departure from controlled flight and possible spin entry. Similarly, simulated engine failures should not be performed during stall entry and recovery. It is recommended that stalls be practiced at an altitude that allows recovery no lower than 3,000 feet AGL for multi-engine airplanes, or higher if recommended by the AFM/PO. Losing altitude during recovery from a stall is to be expected. Power-off approach to stall, approach and landing. A power-off approach to stall is trained and checked to simulate problematic approach and landing scenarios. A power-off approach to stall may be performed with wings level, or from shallow and medium bank turns, 20 degrees of bank. To initiate a power-off approach to stall maneuver, the area surrounding the airplane should first be cleared for possible traffic. The airplane should then be slowed and configured for an approach and landing. A stabilized descent should be established, approximately 500 fpm, and trim adjusted. A turn should be initiated at this point, if desired. The pilot should then smoothly increase the OA to induce a stall warning. Power is reduced further during this phase, and trimming should cease at speeds slower than takeoff. When the airplane reaches the stall warning, for example, oral alert, buffet, etc., the recovery is accomplished by first reducing 1. Wing leveler or autopilot. 2. A. Nose down pitch control. B. Nose down pitch trim. 3. Bank. 4. Thrust/power. 5. Speed brakes/spoilers. 6. Return to the desired flight path. Stall recovery template. 1. Disconnect. 2. A. Apply until impending stall indications are eliminated. B. As needed. 3. Wings level. 4. As needed. 5. Retract. Figure 1219. Stall recovery procedure. The OA until the stall warning is eliminated. The pilot then rolls the wings level with coordinated use of the rudder and smoothly applies power as required. The airplane should be accelerated to Vx, if simulated obstacles are present, or Vy during recovery and climb. Considerable forward elevator/stabilator pressure will be required after the stall recovery as the airplane accelerates to Vx or Vy. Appropriate trim input should be anticipated. The flap settings should be reduced from full to approach, or as recommended by the manufacturer. Then, with a positive rate of climb, the landing gear is selected up. The remaining flaps are then retracted as a positive rate of climb continues. Power on approach to stall, takeoff and departure. A power on approach to stall is trained and checked to simulate problematic takeoff scenarios. A power on approach to stall may be performed from straight and level flight or from shallow and medium bank turns, 20 degrees of bank. To initiate a power on approach to stall maneuver, the area surrounding the airplane should always be cleared to look for potential traffic. The airplane is slowed to the manufacturer's recommended liftoff speed. The airplane should be configured in the takeoff configuration. Trim should be adjusted for this speed. Engine power is then increased to that recommended in the AFM/PO for the practice of power on approach to stall. In the absence of a recommended setting, use approximately 65% of maximum available power. Begin a turn, if desired, while increasing OA to induce a stall warning, for example, oral alert, buffet, etc. Other specified, reduced, power settings may be used to simulate performance at higher gross weights and density altitudes. When the airplane reaches the stall warning, the recovery is made first by reducing the OA until the stall warning is eliminated. The pilot then rolls the wings level with coordinated use of the rudder and applying power as needed. However, if simulating limited power available for high gross weight and density altitude situations, the power during the recovery should be limited to that specified. The landing gear should be retracted when a positive rate of climb is attained, and flaps retracted, if flaps were set for takeoff. The target airspeed on recovery is Vx if, simulated, obstructions are present, or Vy. The pilot should anticipate the need for nose-down trim as the airplane accelerates to Vx or Vy after recovery. Full stall. It is not recommended that full stalls be practiced unless a qualified flight instructor is present. A power off or power on full stall should only be practiced in a structured lesson with clear learning objectives and cautions discussed. The goals of the training are, A. To provide the pilots the experience of the handling characteristics and dynamic cues, for example, buffet, roll-off, near and net full stall, and B. To reinforce the proper application of the stall recovery procedures. Given the associated risk of asymmetric thrust at high angles of attack and low rudder effectiveness due to low airspeeds, this reinforces the primary step of first lowering the OA, which allows all control surfaces to become more effective and allows for roll to be better controlled. Thrust should only be used as needed in the recovery. Accelerated approach to stall. Accelerated approach to stall should be performed with a bank of approximately 45 degrees, and in no case at a speed greater than the airplane manufacturer's recommended airspeed or the specified design maneuvering speed, VA. The entry altitude for this maneuver should be no lower than 5,000 feet AGL. The entry method for the maneuver is no different than for a single-engine airplane. Once at an appropriate speed, begin increasing the back pressure on the elevator while maintaining a coordinated 45 degrees turn. A good speed reduction rate is approximately 3 to 5 knots per second. Once a stall warning occurs, recover promptly by reducing the OA until the stall warning stops. Then roll the wings level with coordinated rudder and add power as necessary to return to the desired flight path. 12 to 27. As very few twins have ever been spin tested, none are required to. The recommended spin recovery techniques are based only on the best information available. The departure from controlled flight may be quite abrupt and possibly disorienting. The direction of an upright spin can be confirmed from the turn needle or the symbolic airplane of the turn coordinator, if necessary. Do not rely on the ball position or other instruments. If a spin is entered, most manufacturers recommend immediately retarding both throttles to idle, applying full rudder opposite the direction of rotation, and applying full forward elevator/stabulator pressure, with ailerons neutral. These actions should be taken as near simultaneously as possible. The controls should then be held in that position until the spin has stopped. At that point, adjust rudder pressure, back elevator pressure, and power as necessary to return to the desired flight path. Pilots should be aware that a spin recovery will take considerable altitude, therefore it is critical that corrective action be taken immediately. Spin awareness. No multi-engine airplane is approved for spins, and their spin recovery characteristics are generally very poor. It is therefore necessary to practice spin avoidance and maintain a high awareness of situations that can result in an inadvertent spin. In order to spin any airplane, it must first be stalled. At the stall, a yawing moment must be introduced. In a multi-engine airplane, the yawing moment may be generated by rudder input or asymmetrical thrust. It follows, then, that spin awareness be at its greatest during VMC demonstrations, stall practice, slow flight, or any condition of high asymmetrical thrust, particularly at low speed/high OA. Single-engine stalls are not part of any multi-engine training curriculum. No engine failure should ever be introduced below safe, intentional one-engine inoperative speed, VSSE. If no VSSE is published, use VICE. Other than training situations, the multi-engine airplane is only operated below VSSE for mere seconds just after liftoff or during the last few dozen feet of altitude in preparation for landing. For spin avoidance when practicing engine failures, the flight instructor should pay strict attention to the maintenance of proper airspeed and bank angle as the student executes the appropriate procedure. The instructor should also be particularly alert during stall and slow flight practice. Forward center of gravity positions result in favorable stall and spin avoidance characteristics, but do not eliminate the hazard. When performing a VMC demonstration, the instructor should also be alert for any sign of an impending stall. The student may be highly focused on the directional control aspect of the maneuver to the extent that impending stall indications go unnoticed. If a VMC demonstration cannot be accomplished under existing conditions of density altitude, it may, for training purposes, be done utilizing the rudder blocking technique described in the following section. 12 to 28.